Cool. Okay, so yeah, let's discuss things that for today's topic. So last time we are basically discussing some kind of the very basic the OpenGL the based the rendering the pipeline, which is basically utilizing the rasterization, the idea, and also we discussed some kind of some ideas in terms of how we can extract some kind of the 3D transformations using especially the 3D rotations using the quaternions. So those are basically some of the kind of images that we can easily render using some kind of the OpenGL-based code. You can say that it looks kind of okay with some kind of the simple, the shape, and also kind of the texture and the color information. We can basically render some kind of some 3D object into the 2D images. And these are typically something that you can also basically get as kind of the outputs of the assignments of the introduction to the course. In the CS380 course, basically all the assignments are basically implementing something using the OpenGL and basically getting this kind of the outputs, which is actually involving quite much some kind of the programming. You should be able to basically program all the things in the vertex shader and the fragment shader, many kind of the complicated things. You also should be able to basically manipulate all this object in terms of the transformations, which means that you should have some understanding for the quaternion, many things. But you might be kind of disappointed that actually the output of all the kind of complicated the programming, it turns out that we are getting this kind of the quality of the outputs. Actually, what we are basically expecting as kind of the output of the rendering is this quality of the images, right? So this is not a real photo, but some kind of the output of the rendering, where you can see some kind of the very realistic, photorealistic details in terms of like having some very details of all the geometry, but also having the lighting and the shading and the shadows, and basically having all this kind of some high details, some kind of quality in terms of like all the part of the images. So the focus of like this course is basically how we can achieve this kind of the rendering the outputs by switching the rendering the pipeline. So that's basically what we are going to discuss in this course. So what we have discussed in the previous time is basically the rasterization of the pipeline, while what we are going to discuss today is more about the ray casting and also the ray tracing. So the difference between the rasterization and the ray tracing is actually nothing, but it's more about like whether we're gonna basically project all the things in the 3D into the 2D plane first and do some kind of the process in the 2D plane. Or we're gonna basically not just like projecting things into the 2D plane first, but actually shooting the ray from the camera through the 2D plane into the 3D space. In terms of that, basically not just like projecting things, but kind of like fetching some kind of the color or some kind of the material information from the region where we are basically seeing some kind of the intersection between the ray and the 3D objects. So that's kind of the major difference between the rasterization and also the ray casting and the ray tracing. So if you see a little bit more details about each of the algorithm, the rasterization, the pipeline typically has this kind of form. So as we discussed in the previous lecture, what we are basically having is that we first basically initialize the Z buffer, which is having the same size with the rendered image. And for each of all the triangle, we are projecting those triangle into the 2D plane. And we start to care about each of the pixel inside the triangle, which is also called the fragment, right? So for each of the fragment, we are basically interpolating all the information that are basically defined for each of the vertices of the triangles. So interpolating the information defined at the vertices of the triangle in the 2D plane, define some kind of the color information and also the depth information. And if the depth information that we are calculating is basically closer than the depth that was stored in the Z buffer, then we are basically updating the information in the image. So this was the very typical idea, the pipeline of the rasterization. It is clear. So this was basically something that we discussed last time. So we first project all the 3D triangles into the 2D plane. And for each of the triangle, we start to see what are the pixels that are included for each of the projected triangle. And in the 2D plane, we are interpolating the information that are defined over the vertices that will basically determine the color and the depth, many things for each of the pixel. And basically, we are getting the depth information from the interpolation of the triangles. And if this depth information is basically closer than the depth that we are having in the depth buffer, then we are replacing the information the color and the depth information for each of the pixel. So we keep iterating this kind of process for every single bit triangle for the also to update all the pixel information. So this is the very typical framework for the rasterization. And what we can see is that actually the ray tracing and also the ray casting is kind of the opposite. So we start to care about all the pixels, not all the bit triangles. So for every single pixel, what we do is that we are now shooting a ray from the camera center, making the ray which is passing through each of the pixel, and see where this ray is basically intersecting with some kind of 3D objects. So if we see some kind of the intersection between the ray and some 3D object, then we can now retrieve some kind of the color or the many other information from that the point we are seeing the intersections. So in that way, we can basically update each of the pixel. So this is kind of a different way that we are basically updating each of the pixel information, which sounds kind of very similar with the rasterization, but we're gonna see what's kind of the advantage like this kind of approach. It is clear the difference between the rasterization and the ray tracing. So in the rasterization, it's basically object first. For each of the objects, we are projecting them, and then see what are the pixels that are included for each of the triangle, and basically updating all the pixel information. And the ray tracing is basically the pixel first. So for each of the pixel, we shoot a ray and see at which point over the 3D object we are making some kind of intersection between the ray and the objects, and then fetching the color or the many other information from the point of the 3D objects to update the pixel information. So that's kind of the major difference between the rasterization and the ray casting. Actually, this ray casting is basically a very old idea, which was first introduced in the 1968, which is 56 years ago. So it's quite a very old idea. So it's just basically the idea that we are kind of like simulating the lighting kind of this optical the process. So basically the ideal case that we are really simulating the optical process might be is actually starting from not from the camera, but actually starting from the light source. So as you can see, if we really wanted to have some very precise simulation of the optics, what we can do is that we are really simulating all the kind of the light traversal. So starting from the light source, we are shooting all the rays of the light and see where basically these rays are basically intersecting with the 3D objects, and also basically tracing all the kind of the rays in terms of like what are basically the rays which are basically reaching to the image plane. So in a way that we are really basically simulating all this kind of the traversal of the rays that are basically reaching to the image plane, and then basically calculating all the color information. But the problem like this kind of the process is that there might be a very small amount of the rays which are really arriving to the image plane. So there might be very low kind of the hit rate in terms of like when you see like how many of the rays are really basically coming back to the basically image plane, there might be very few number of the rays, which means that the computation will be very inefficient. So in terms of like handling this kind of like inefficiency, actually we go in the other way around. So we are not starting from the light source, but actually we are starting from the image plane, which means that we are basically back tracing all the rays from the image plane to the light source. So what we can basically do is that instead of like shooting the ray from the light source, now we are shooting the ray from the eye point, from the camera center. For each of the pixel, we are basically shooting the ray and check the intersection point with any of the 3D objects. So as you can see here, we are shooting the ray here, and we see some basically intersection point here. And the way that we can basically update the pixel information might be is that we can somehow retrieve some kind of the color or some any other information from this point, which will basically update this pixel information, right? But here, basically, what we also want to do is that we also want to determine the color information not only based on some kind of inherent kind of property of this surface, but also based on the light here. So what we actually do is that we are not only basically checking this point, but we actually shoot a ray again to the light source to check whether this point not only visible from the eye point, but also from the light source. Which means that if there are some kind of the occlusion, which is basically occluding this point from the light source, then this point will not basically receive some kind of the rays from the light source, right? Which means that this point will be dark. So we should not basically bring some kind of color information from this point. So basically what we are going to actually discuss in the rest of this course is that basically how we can model this kind of the reflection kind of things in terms of like when we calculate the color information at this point, we are not only basically caring about some kind of the surface property at this point, but also some kind of the light information from here. And also checking whether this point is also visible from the light source as well. In terms of that, we can calculate the color information based on this surface property and also the light source property, and then updating this pixel information. So for some more details about the reflection the system in terms of how we're going to really calculate the color at this point using both the surface property and the light source property, we can also discuss all these kind of things in the rest of the course. But this is basically the basic idea for the ray casting, which is basically caring about the light source in terms of like, updating the color information. It is clear? Any questions on this? So this is basically the basic idea for the ray casting. But the thing is that if we really wanted to have some, precise the simulation for the optic system, the light reflected at this point would not just like come from directly from the light source, but there can be some many other kind of the passes that is like coming the light from the light sources to this point, right? So there can be many other ways around basically somehow, I don't know, make some kind of reflections with some other 3D objects, and also the light arrives at this point. So to basically handle all these kind of the cases, actually we should be able to be basically iteratively update this kind of the ray information. So what we typically do is that we are not only basically caring about the hit point. So let's say when you shoot the ray from the camera center to this 3D space, and this might be the first point that we are seeing some kind of the intersection. Then also what we can do is that we are also checking where the ray basically should be reflected using some kind of the reflection model as well. Yeah. So basically, when you have some kind of speculative reflection, then we can calculate where the ray should be reflected to, like this, right? Then we are also having another intersection into the 3D objects. And we can repeat this process, right? So until we have some kind of speculative reflections over the 3D surfaces, we can iterate having this kind of the second ray, basically having another intersection with the 3D objects in terms of like tracing all the paths of the 3D objects into the 3D space like this. So as you can see, this is the case that we're having some reflection. So the ray is basically reflected over the surface. And this is another case that we are basically seeing some kind of reflection, which is the case that even the ray is like passing through the objects, which is basically making another branch of the rays. So we keep iterating all this kind of like the process, basically shooting the second ray. In terms of that, we are really reaching to the either the light source, where we are basically reaching to some kind of the maximum iterations. And then now we can calculate the color of each of the pixel here by accumulating the color information that we are calculating all the intersection point. And when we basically determine the color information for all the intersection point, we also shoot the ray to the light source to check whether this point is really basically visible from the light source or not, whether we have some kind of the occlusions here or not. So based on whether this point is basically occluded or not, we can also determine the color information at this point by combining the material information at this surface and also the light information, which is basically seeing this point. So this kind of the iterative process, like basically, really, traversing, tracing all this kind of path of the rays are basically called the ray tracing. So the difference with the ray casting is that ray casting is the case that we only care about the first intersection point. And at this in like first intersection point, we determine the color information by shooting the ray to the light source, which is called the shadow ray. And the ray tracing is not only caring about the first intersection point, but we also really trace this kind of traverse of the rays by shooting the second ray, which is basically determined based on the reflection of the model. So at this point, we shoot the second ray, which is the direction is determined by the reflection kind of the model, and also the another ray based on the reflection as well. So we keep iterating all this process in terms of like having this kind of the trajectory, all the rays. And for every intersection the point, we also shoot the shadow ray to the light source to determine all the color information. And the pixel, the color information is basically determined based on some kind of the linear combinations of those colors. So this is kind of the ray tracing system. Any questions on this? So as you can see, especially when you see this kind of like ray tracing the system, the major difference with the rasterization is that for the rasterization, we cannot really deal with this kind of the some kind of the light interactions with the surface. So since we are basically shooting the LED ray into the 3D space, and also since we can trace all the rays into this kind of the second rays in the path, now we can really calculate this kind of we can do some kind of more precise sort of the optic simulation in terms of precisely determining all the color information, and also finally basically calculating color information for each of the pixel. But in the rasterization, since everything is basically just like projected into the 2D plane, we cannot really have this kind of the calculation, which is really caring about this kind of the ray and the object, the intersection, and also updating the color information based on the light source. So which means that the ray tracing can be kind of the rasterization can be some kind of the faster system, which is also typically basically accelerated by some kind of the hardware implementation, but this cannot be some kind of the accurate, some kind of the rendering the system in terms of that we cannot track all the lights in the 3D space. And compared to the rasterization, the advantage of the ray tracing is that this is becoming more accurate, some kind of simulation of the light traversal. But obviously, it is having like more the computations in terms of having the second ray and also the shadow ray for some more kind of the precise the computation, which is involving much more the computation, and also the computation becomes like much more the expensive. So that's the basic idea, and also the comparison based on the rasterization and also the ray tracing. Any questions on this? So how long does it take some time? So if we actually go back to this kind of the very basic kind of the rendered image. So this is basically the image which was first introduced in the 1979, some years ago. So as you can see, this was kind of the first kind of the rendered image which could be able to basically handle this kind of the transparent object. So with the rasterization the pipeline, it is impossible to have this kind of the some sort of transparent object, because we don't know how we can deal with these kind of things in the rasterization the pipeline. But in the ray tracing the pipeline, we can basically shoot the ray not only basically having the reflection over the surface, but making the ray to be to pass through inside the object and having some more the precise simulation. So now we can start to render this kind of the sort of the transparent object in the scene. So this was kind of the first image, which was basically rendering some kind of the transparent object using the ray tracing the system. And at that time, when this image was introduced, it was taking 74 minutes to render this simple image, which is taking lots of the time. But after like some decades later, using some kind of the better the computer, now we can render those kind of things in the 6 seconds. And if we use the GPU, now actually it takes like real time, basically taking like 1/30 of the seconds. But how about like if we have some more the complicated kind of things? So in the sort of the history of the computer the animation, one of the kind of the famous example, like which is fully utilizing this kind of the ray tracing the system, is this animation, the KAIST from the Pixar, which was released in the 2006. So actually, some kind of the characteristic of like this animation was that this was kind of the case that there are lots of some kind of these 3D objects that have this kind of specular the materials over the kind of the surface. So basically, all the curves are basically having the metals, which means that all the surfaces are basically some specular materials. Which means that we really need to calculate this kind of the reflection of the rays of the surface, which will involve lots of the computation. And this is also the animation that you can see tons of the colors in a scene. So actually, if you see how this animation was created, actually they were taking tons of time for the computation. So even for like rendering a single frame of the animation, they said that actually sometimes it took like in average, it took 17 hours using the machine at the time. And sometimes just like to render a single frame, they said that it took like a week. So which is kind of the output of the super heavy computation for every single frame. So this was kind of the sort of the extreme case of like fully utilizing all the ray tracing the system to get some very precise and realistic images by simulating all this kind of the ray traversal. Any questions on this? So basically, in the programming the assignments, what you will need to do is basically implementing the very basic system, which is rendering the images using the ray tracing, the pipeline. And the first step to basically implement this kind of like ray tracing the system is basically to implement the ray surface in the intersection. Obviously, this is the first step. So for each of the camera model and to the image plane, sorry. So like the task 0 in the programming assignment is to basically shoot a ray from the camera to the first to the image for each of the pixel in the image plane. And then you should be able to basically check whether this ray is basically intersecting to the any of the 3D object in the scene, and what's the exact point that we are having the intersection. So we should be able to calculate these kind of things. Which is actually a very essential task, not only for the ray tracing the system, but for the many other things. So this is also required not only to check the intersection between the ray from the camera to the 3D objects, but also when you shoot the shadow ray, when you also shoot the ray from the object to the light source and check any kind of the occlusion, you also need to have this kind of the process. And also many for many other some kind of the geometry processing, this kind of the some ray intersection the check is kind of the very the essential in the basic task. So this is like very simple, but basically type, probably very, very slow the task. So for every single the ray and also every single discrete object, you should be able to check this kind of intersection. So let's do some kind of the simple calculation. So let's think about this case that we are having a ray, which is starting from this point. So I will denote the origin of the camera center as kind of the O tilde. And we are shooting the ray into the D direction, so which is the vector here. So now the ray equation can be defined like this, right? So for any kind of the time t, which is like 0 or the greater than 0, we can basically specify the point over the ray, right? We now define this kind of the ray equation. So it's kind of the simple example. Let's think about the case that we are checking the intersection between the ray and the plane. So now the plane is defined with the any of the point over the plane, which is actually the tilde here, and also the normal direction over the surface. Then here the simple the question is that if we assume some kind of the infinite plane with any of the point and the surface normal, then how can you calculate the intersection between the ray and the plane? So this is the first question. So please post your answer over the slide. So let's think about the case that we're having this ray equation and also the plane equation. Then how can I calculate the intersection between these two? So just to clarify, like what I explained about the ray tracing, so the thing is that like if we shoot a ray from the camera through the image plane and see some kind of intersection with some 3D objects, uh, so yeah, I mean then no, based on this intersection, the point, we will determine the color information at this pixel, right? But what we do is that we do care about basically the lighting. So how much the light basically affects the color at this point. So we're gonna discuss this kind of the some reflection, the model in terms of like how we determine the color at this point based on the material information and also the light information. Which means that we need to check whether this point is visible from the light source or not, right? So if we have this like the ray and the intersection the point, and then we shoot a ray from this point to the light source in terms of to check like whether this point is also visible from the light source or not. And this ray that we are shooting from the intersection point to the light source is called the shadow ray. So if this was the ray, which was basically the ray from the camera to the object, and this is the ray from the object to the light source. This is to basically check whether this kind of the light source is basically visible from from this point or not. So if this light source is visible from this point, then now we can basically determine the color information based on this material and the light source. Or if this point is not visible from this light source, then this is not the light, which is basically determining the color information at this point. So this point should be dark. This is the only light source. But there can be actually multiple the light sources as well, which means that we also need to shoot the shadow ray the multiple times. And if we also stop like shooting the ray at this point, and that's it, then this is the case that we are having the ray casting. But if we also recursively like shoot the ray based on the reflection at this point, so if we have the plane, like that's what we also learned in high school, like if we have the incoming ray at this point with incident the angle here, then when this is the normal direction, then we can also see that the ray is basically reflected with the same amount of the angle here, right? So based on that, we can also define some this kind of the some reflection of the ray at this point, and we can recursively repeat this process, like shooting the ray again, finding another intersection the point, and shooting the shadow ray again. So if we have this kind of the recursive the system, this is the case that we are having the ray tracing. So this is kind of the terminology that we are using in the graphics. So just keep this in mind. Yeah, so this is basically what we are doing. So for that, we need to be able to basically calculate the intersection point. And obviously, if we have the calculate intersection point of these two, then we can basically calculate the time t like this. So if this time t is negative, which means that the plane is only the behind of the ray, right? So there is no intersection point. So we are having the intersection point when only the t is basically 0 or greater than 0. So this is basically the case that we are having the intersection. So this is clear, right? And also this kind of the ray and the plane intersection becomes like much simpler if we have the axis aligned the plane. So we're gonna also see this kind of cases that we are having the axis aligned the plane. But if we have this kind of like axis aligned plane, then for example, like when you have the plane which is parallel to the YZ plane, having this kind of the plane, then the intersection becomes can be calculated into this simple form. So these are also kind of all the simple the calculation. The question is that do we recursively create both a reflection ray and a reflection ray for each intersection point? Yes, actually it depends on the property of the material. So we're gonna also discuss that point. So here the question is that whether we really create both the reflection and the reflection of the ray. So it depends on how we define the material the property. So we're gonna get into this in the rest of the lectures. Any questions for the ray tracing, ray casting, shadow ray, second ray? So what we mean with the second ray is basically when you shoot the second ray from the recursion in the ray tracing system, that's the case that we're having the second ray. Yeah, so this was the case that we are calculating the intersection between the ray and the plane. But actually, what we also have seen in the previous lecture is that we typically represent a 3D object as kind of the set of the triangles, right? So the typical the case that we are having the lots of the triangles in the 3D space, which means that we should be able to calculate the intersection not only with the some infinite the plane, but with this kind of the finite the triangle over the plane. So here the question is that how we can really check whether the ray is really intersecting with the triangle, which means that when you find the intersection the point with the ray and the plane, we should be able to also check whether that point is included in the plane in the triangle or not. So this is kind of another calculation that we need to do. So the kind of the simplest way that we can really check the intersection with the triangle, not with the plane, is to leverage the barycentric coordinates. So we briefly discussed the barycentric coordinates in the second lecture, but let me briefly review this idea. So let's first see the line interpolation. So when you have the 2 points, P1 and the P2, what we can see is that any point over this line segment connecting these 2 points. So given any 2 points and the P1 and the P2, any point over this line segment connecting these 2 points can be actually represented as kind of the linear interpolation between these 2 points, right? So when the ratio like in the D segment and the this segment is then the T and the 1 minus D, then these points interpolating these 2 points can be calculated like this, right? So this is the case that we're having some linear interpolation. So the basic idea for the barycentric interpolation is to basically having this kind of interpolation not only for the line, but also for the triangle as well. So let's think about the case that now we are having the 3 points and defining a triangle. We're having the P1 and the P2 and the P3. Then any point P tilde over the triangle can also be represented as kind of some linear interpolation. Having the like 3D parameters, 3D coefficients, let's say this is kind of, I don't know, like A, and also the U and the V. And what we can see here is that, as we can also see in the previous line interpolation case. So let me briefly go over this. So here, basically, when you take some kind of the interpolation between the 2 points, the sum of the coefficients should be 1, right? So as you can see, when you have the coefficients for the P1 and the P2, the sum of the coefficients should be 1. So that's kind of the constraint to have some kind of the interpolation. And also the thing is that each of the coefficients should be also greater than 0, right? Or same or greater than 0. So that's the case that we're having the interpolation. Otherwise, if we also allow the negative coefficients, then what's such kind of the case? If we start to allow some kind of the negative coefficients, then what's the case? Yeah, I mean, if we start to allow the negative coefficients, that's the case that we are starting to see some kind of the extrapolation, right? Very obvious thing. I mean, which means that now we are having not only points inside this line segment and also having the points outside of this line segment, but also still on the straight line. And also this kind of the case where the sum of the coefficients are basically the 1, and also each of the coefficients is basically non-negative the number. So those are the cases that we are having the convex interpolation. So when you have the convex interpolation for these 2 cases, where we are basically drawing some kind of the line, which is connecting these 2 points. So which is kind of similar in the triangle case as well. So when you have the 3 points, having the 3 coefficients for each of the point, if the sum of the coefficients is 1, and also each of the coefficients is non-negative the value, for those cases, basically having the convex interpolation, if we have the convex interpolation, then we are basically defining a triangle, which is connecting these kind of 3 vertices. Is this clear? And also, I recommend you to check this out. But the thing is that this kind of the weight, the coefficients for each of the point can be actually determined based on the area. This is also what we discussed last time. For example, like the coefficients for the second point, P2 here, can be defined as kind of the ratio of the triangle, the area, basically using the P1, P2, P3, and then P tilde, P1, and P3. So the area of this part, which is the opposite of this point, over the entire the triangle. So this ratio basically becomes the coefficients at this point. So I recommend you to check this out, how we can really prove this. So those are kind of the way that we can define some kind of the interpolation over the triangle. So here basically the thing is that any kind of the point over the triangle defined with the three the vertices are basically defined based on the three coefficients, the coefficient for each of the vertices. And these three the coefficients are called the barycentric the coordinate. So what this means is that for any point over the 3D the space, if that point is included in the triangle defined with the three vertices, we can either represent the point with the x, y, z coordinates, or we can represent the same point based on the three the coefficients defined for each of the P1, P2, P3, these three vertices. So that's the another way that we can basically express the position of the point, especially when the point is located inside the triangle. Is this clear? And from the constraint that we know that the sum of these three coefficients should be 1. Actually, we can drop one of the coefficients here and having the only the two the parameters. Sorry. Yeah. So instead of like having the three D parameters, we can make this to be 1 minus u minus v, and just having the two parameters. Which means that now we can even express any of the point, not with the 3D numbers, but with the two numbers, u and the v here. Make sense? Is this clear? Then what we can do is that we can just like plug in this kind of the barycentric the equation of each of the point into the ray equation. Then we can see these two should be the same. So the left-hand side is basically the equation for the ray, and the right-hand side is basically the equation based on the barycentric the coordinates. So based on this kind of the constraint that these two should be exactly the same, we can just solve this kind of the linear equation with the three parameters here. So if we basically solve this kind of the linear the system, we can determine the t, which will also determine the position over the ray. It is clear. Here, one quick question is that what would be the case that this matrix is not invertible, so we cannot have any kind of solution? So what would be the case that we cannot have some unique solution? Question? So what is kind of the case that this matrix is not invertible, so we cannot specify the unique solution? I mean, there are multiple such kind of cases, but one case might be is that the triangle has the zero area. That's kind of also the exception of the case. But if we do not such kind of some extreme cases, that we have some kind of the non-zero area, the kind of triangle, then as you can see, like these are kind of the two vectors which are spanning the subspace, defining the plane that includes this kind of the triangle. If this matrix is not invertible, which means that this direction of the ray is basically dependent to the subspace of those two vectors, which means that this direction of the ray is basically the parallel to the kind of the image plane, the triangle, sorry, here. So when the ray is basically the parallel to the triangle, that plane, we cannot find the intersection point. So that will be one of the cases that we cannot determine the unique solution. There is no solution for that case, right? So for those kind of cases, this matrix will not be invertible and we cannot solve this linear system. And also based on the output of the T and the U and the V, if we find this intersection point, then all this kind of constraints should be satisfied, which means that T should be non-negativity number, and also the U and the V should be the number inside the 0 and the 1 range, right? And also the U plus V should be in this range. So when we satisfy the kind of the outputs that satisfy all these kind of the constraints, then we can see that those are the cases that we are finding some kind of intersection between the ray and the triangle. Some simple calculations. So let's do one more kind of some simple calculation. So by the way, those are kind of also the things that you will need to implement if you're deploying the assignment. Another some kind of simple calculation is that if we have the ray and also the sphere as well, like sphere as some kind of the primitives. So the case is, when we want to see some kind of the sphere as kind of the primitives, is that sometimes we also represent some kind of 3D objects as kind of a set of the points. So we call those kind of things as kind of the point cloud. So when you have the point cloud, sometimes we might also want to assign some kind of the volume for each of the points. That might be the case that we are representing each of the point as kind of the sphere, as you can see here. Or actually, those points can be represented as the disk or the ellipsoid, all the things. Actually, the case that I mentioned at the very beginning of the lecture, having the Gaussian split, those are actually the cases that we are representing each of the point as kind of the ellipsoid, which is slightly more complicated than this. But let's think about the simple case that we are having some kind of a set of the points, but actually each of the points are not just a point, but having some volume, so which can be represented as a sphere. So if we have the ray and the sphere, then also how can you find the first intersection the point? Let's also work on this question. Yeah, two. So did you get this kind of quadratic formulation? So you will see that actually we are getting this kind of the quadratic formula. So if we solve the quadratic formula, then there might be three cases. So if there is no solution, which means that there is no intersection between the ray and the sphere. And if we also have the solution having the single solution, there might be the case that the ray is basically having the intersection the point at the single point like this. Or typically we're gonna see this kind of the cases where the ray is basically intersecting at the 2 points over the sphere. So we can pick the point, one of the two solutions, which is like having the smaller t, but still the non-negative t. So that might be kind of the first intersection point between the ray and the sphere. Right? So for any kind of the primitives, we can consider basically solving all those kind of things and then finding the intersecting point. So also for the fast computation, it might be the matter of like how we can efficiently compute all the kind of things. One more case might be is that now we can also consider like representing all these 3D objects and the scenes not as some kind of some explicit objects, but as kind of some implicit surface. So we can also get into the idea of like having the implicit surface later, especially for these neural rendering things. But those are some of the cases that we are now representing all these kind of the 3D objects in the scene, not as some kind of the mesh or the point cloud, but actually as a the function. You see, there are also the multiple ways that we're having some implicit representation. But for example, we can represent this kind of sphere as kind of like this kind of some implicit function. So if we say that like when you calculate this, if this number is basically greater than 1, which means that that point is outside of sphere, right? And if that point is like less than 1, that means that the point is inside of the sphere. And only when these two are basically the same, you can see that the point is exactly over the surface. So like having this kind of the formulation for each of the objects can be one of the way that we can represent some of the 3D objects in a kind of the indirect way using some kind of the formulation. This is kind of the implicit representations, and we also call implicit surfaces. So when you also have this kind of like implicit surfaces, how we can basically find the intersection point between the ray and this kind of the objects? Well, the simplest way is that we are basically marching the ray. So from the starting point, like along this direction, like we are basically making some kind of steps. And every step we can check whether the point is exactly over the surface or not. And if the point is basically having the positive, the kind of value with the function, which means that the point is outside of the objects, then we can go one step further, right? And we can basically create this kind of process until we have that this value becomes 0. So this is kind of the simple idea in terms of like how we can find the intersection point between the ray and the implicit surfaces. But actually, there can be some more efficient way, especially when you have this kind of some signed distance representation. So here, basically, signed distance means that we are having some kind of the function which is taking any kind of point over the surface, over the space. In terms of that, this function is now representing if this value is basically positive, which means that the point is outside. Negative means that the point is inside. And if the point is 0, then that means that the point is exactly over the surface, right? So this is kind of the sign distance function representation for the 3D objects. And if we have this kind of the sign distance function, what would be kind of the efficient way that we are doing some kind of the marching the ray over this space? Any ideas? Yeah, so let me just move on this. So the simplest kind of the way is to this kind of like sphere tracing. So here the basic idea is that let's say we start from here. And let's say we fetch the kind of the signed distance value. And if this distance is basically negative or equal to 0, then we can stop marching the ray. But if this value is greater than 0, which means that, so let's see, if this is like greater than 0, actually this means that the closest point from this point to any of the point over this surface might be this. So when you basically measure the distance from this quarry point to any of the closest point over the surface, that becomes our defined distance, right? This basically means that it's now safe to merge the array with amount of like this distance because like until this distance in this pair, there should be no obstacles in this 3D scene. If there are some kind of any objects here, which means that the signed distance should be shorter than this. Does it make sense? I mean, it's basically a very simple idea. So every point, we are basically calculating the signed distance. If this distance is zero or the negative, then we stop the merging, right? But if this distance is basically the positive, let's say having some kind of the distance d, then which means that in this pair defined with the radius of the d, there should be no any kind of the some obstacles. Because if there are some obstacles, then this distance should be smaller than d, right? So it's safe to merge the array until like the end of like this pair, the bound of this pair. So we go this step, and then we calculate the sign distance again. And then also define this pair, and we iterate this kind of merging. Right? So this can be slightly more efficient way in terms like, we are seeing how much we can basically proceed this kind of merging based on the sign distance we are getting for every single point. That makes sense? So this is the basic idea, which is called this pair tracing. And can you guess some kind of some extreme cases that this kind of the process becomes like very inefficient? Any of those? Actually, this is already showing some kind of the extreme cases. But for example, like we are shooting the ray in this direction, and some objects are basically having this kind of the shape. Then what we can see is that this ray should have the intersection at here, right? But actually, no, on the way to going to this intersection, the point, we are basically approaching to this region, which basically making the signed distance to be very small. So at the very beginning, the sphere will be big like this, right? But as you go further, we're going to have a very tiny sphere, which means that as you get closer to the any kind of some kind of surface over the objects, the kind of the interval of the margin becomes also the smaller. So actually we get very small, slower here, and then we get some kind of the bigger sphere like this. So depending on what sort of the objects and also the ray direction that you have, actually this sphere tracing can even become, less efficient than some kind of the other the ideas. So there can be some kind of pros and cons, so like having this kind of the approaches. Any questions on this? Great. Yeah, so these are all the examples that we are checking the intersection between the ray and some of the objects in the scene that are defined as kind of the plane, triangle, sphere, or implicit representations. But here also the question is that how can you also accelerate this kind of the computation for the intersection? So because like what we need to end up doing in the ray tracing the system would be is that for every single the pixel, and also every single the objects, for all these kind of the combinations, we will need to basically check this kind of the intersection. So depending on the number of the rays, basically number of the pixels and the number of the objects in the scene, this computation will be extremely heavy. Like some kind of example is that this is a kind of scene which is basically rendered using some kind of the ray tracing the system. And can you guess how many triangles do we have in this thing? To represent all the details in the leaves, like all these kind of things. I don't know, also for some kind of fine details over the back part of the chair, how many triangles do we need? Can you guess? Any guess? Like how many triangles do we have? Yeah, 1 million, 2 million, 10 million, 500K? Actually, this is the case that we are having the 10 millions, 10.7 billions of the triangles. So which means that we have some hundred thousands of the pixels and having the 10 million of the triangles. We need to calculate all the intersections for all the combinations like these two, which will be extremely heavy, right? This is another even more extreme case. We are having the 20 million triangles. Like having this kind of like millions of triangles is quite common in many kind of some graphics, some kind of the outputs. So here the question is that how can we efficiently basically compute all these kind of the intersection in a way that we can boost up the ray tracing the system. So the basic idea for those kind of the acceleration in the computation is to have some kind of the bounding the volumes. So the basic idea for the bounding volume is that we are encapsulating some of the 3D objects using some kind of the primitives that we know it becomes like much simpler to calculate this kind of the intersection. So for example, like when you have this kind of like some complicated shape, we are basically encapsulating this kind of objects into the simple the bounding box in a way that the computation of the intersection becomes with the ray and the bounding box becomes like much simpler compared to like computing the intersection with the ray and some real discrete objects. So what kind of the primitives can you use? We can also use the sphere because we also already know how to compute the intersection with the sphere, and box is whatever anything that we want to do. One of the kind of the ideas is using the axis aligned the bounding boxes. So if we use the axis aligned the bounding boxes, then what we need to do is that we can see that actually all the boxes can be represented as kind of the 3 pairs of these slabs. So for each of the x, y, z axis, we are having the 2 parallel planes. So in the 2D case, for example, here, we are having this pair and another pair, right? And in the 3D case, we're going to have the 3 pairs of the slabs. And we have seen in the previous slide that computing the intersection with the axis along the planes is really simple, right? So this becomes really the simple calculation. So given this kind of the intersection with the 3 pairs of these slabs, which is basically giving the kind of the minimum and the maximum the values of the time for each of the ray, we can check whether the ray is basically intersecting with the bounding box or not. So what this basically shows is that for each of the axes, so this is the case that for this axis we are having this slab and this slab. Given these 2 slabs, we can basically see the intersection point, 2 intersection points, which are represented as the T min and the T max. And we can compute this kind of the range of the time for each of the axes, right? So for each of the axis, we're going to have the T min and the T max. For the x and the y, we're going to also have this range, and also g, we're going to also have this range, right? And given this kind of the 3D ranges of the times, how can you check whether the ray is intersecting with the box or not? Another question. Yeah, basically, if the maximum of all the t mean values for each of the x and the y and the z is basically t mean y, t mean z becomes basically smaller than the minimum of the t max for each of the axes. That will be the case that we are having some kind of intersection between the ray and the bounded boxes. So yeah, we are running out of time, but I recommend you to check out how we can check the intersection between the ray and this kind of the axis aligned the bounded boxes based on this kind of the 3 ranges defined with the 3 slabs for each of the axes. So yeah, so this is kind of good. So then now we can see, we can basically somehow represent some kind of the groups of the objects using the bounded boxes. And here also the question is that how should we basically define the bounded boxes? So when you have this kind of the scene, should we basically make like one big giant the bounded box that includes everything? Or should we basically make the bounded boxes for each of the objects, right? What would be kind of the best way? So the problem is that if we have like the one big bounded box, so it can be good for some of the cases that like when the ray does not hit any of the objects. So if the ray does not hit any of the objects like this, then we can just quickly check the intersection between the ray and the bounding box. And if we see that the ray is not hitting the box, then we can ignore all the objects in the scene. That's good. But the problem is that if the ray starts to hit the bounding box, which means that now we need to check the intersection with all the primitives included in the bounding box. Then it's not efficient at all, right? Also, the other cases around is that if we have the bounding box for each of the objects, then if we have the n number of the objects, then we're also having the n number of the bounding boxes. Then there is no acceleration, right? So here the basic idea is that, so let's think about the case that we are doing some kind of the binary search in the 1D. So if we have this kind of the sequence of the integer number and given any kind of the query number, let's say, I don't know, like 9 or I don't know, when the k is, for example, like 11 or something, then what's the kind of the best way that we can find some kind of the number in the sequence which is closest to the given the query number? Then what we learned in the algorithm course might be is that we are doing some kind of the binary search, right? So given this kind of the sorted the sequence of the number, we take the median here and check whether our the query number 11 is basically smaller and greater than this kind of the some pivot number. Then we can basically take out all this kind of the parts on the left-hand side. We only care about this, right? And then we pick the median at the subset again and comparing with the query number, just repeating these kind of things. So in this way, we can make some kind of the complexity, the time complexity of the search to be basically log n, right? So here the question is that how can we do the kind of same things in the 3D space as well? So as we basically define this kind of the binary the search tree, we can consider making some kind of the hierarchical tree in the 3D space. In terms of that, we can basically accelerate this kind of the search process. So that's the basic idea of the bounding volume the hierarchy. So here the basic idea is that we are starting from this kind of the big bounding box, and then basically splitting this kind of the biggest set into the two disjoint set. So here the thing is that we are making the two disjoint sets of the primitives, basically dividing the set of the primitives into the two subsets. But still, when you see some kind of the bounding box, those of the two subsets, those bounding boxes can overlap in the space. So what you can see is that this is the case that we are splitting the primitives, not the space. We're going to also see the other way around. So as you can see, starting from the biggest set of the primitives, we split the set of the primitives and making the two bounding boxes, and we can iterate this kind of process in terms of like making some kind of tree. The basic idea for that is that for each of the step of like splitting, we are choosing the axis align the axis, and then we are having some kind of the candidate the split, which is defined as this kind of the half plane the space. So we can basically define this kind of the candidate the split the planes, basically some kind of uniform desampling or adaptive desampling, those kind of things by the basically end point of the primitives. And then given this kind of the candidate planes for the split, we are choosing the best one of the best one, and then we repeat this kind of process for each of the axes, having some kind of the candidate planes for the split and choose one of the best. Now here the question is that, what's kind of the best split in this kind of case? Let me give you some kind of example. So we have this kind of thing, and then we are basically having some kind of the multiple the candidates of the split the planes, for example here. Then how are you going to basically choose the split planes? Can you divide this set of the planes? Any ideas? Yeah, let's make this as kind of the last quiz. what would be kind of the best way to basically divide the set of the primitives into the two subgroups, and why? So since we are running out of time, so let me go a little bit quickly. But so actually the reason that I'm asking this is that if we follow the binary search, that what we need to do is that we're gonna basically pick the median, right? So we are having like sorted the primitives here from the left to right. So we are having the like one, two, three, three. So in the given the order of the sorting, like one, two, three, four, like I don't know, five, six, seven, eight. So since we are having the eight primitives, if we basically divide this into the two sets, then the kind of the if we follow the binary search, then kind of the two sets might be like this and this, right? I mean, if we just like simply just follow the binary search. So this is like basically what we're gonna see when you just like divide this into the two subsets that are basically having the equal number of the primitives, then we're gonna get this. But we can actually see that this is quite inefficient. Why? Because we are having this kind of the big bounding box. So actually, it's better to have some kind of the tight bounding box in a way that so for all the rays that are passing through the empty space, we should not basically check the intersection with any of the some of the primitives, right? So basically, when you have some kind of this sort of the tight, the bounding boxes, we can reduce this kind of the some sort of the false positivity cases where basically the ray is basically intersecting with the bounding box while the ray is actually not intersecting with any of the primitives. So here the key is basically how we can minimize this kind of the sum of the volumes of each of the bounding boxes in a way that we can have some more the efficient system. So for that, basically, we can think about how we're gonna basically, define some kind of the most efficient case, like dividing the bounding boxes. So we can define this kind of the traverse of the cost. So here, basically, this is kind of the constant term, basically checking whether the some kind of the course of the traversal with some kind of the interior denote. So basically some bounding box the test, and then we're gonna also some kind of the cost for the left subtree and also the cost of the right subtree with some kind of the probability whether the ray is really intersecting with the left set the bounding box and also the right set the bounding box. And there are some kind of ways that we can approximate for each of the term here. So since we are running out of time, I'm going to resume those things on Wednesday. But I'd like to recommend you to check this out. Basically, what's the kind of the best way that we are defining this kind of some hierarchical tree with the bounding boxes in a way that we can make some more efficient system that can really accelerate this kind of the computation of the intersection. So let me stop here, and I will basically resume this part on Wednesday. Any questions on this? So especially the things that we discussed today, the ray and the primitive intersection, those are basically things that you will need to implement your the programming assignment. So I recommend you to check out the programming assignment as early as possible and see what the kind of things that you need to implement there. And if you have any questions for the programming assignment, please let us know in the Slack. Okay, then I will see you on next Wednesday. Thank you.